back to the second part of the tutorial. I'm Rebecca, as introduced, and I'm very happy to be able to present here. And I'm going to speak about something I actually did together with the other two people in the tutorial. Divya, you have already seen, and Simon is going to do part 3. So we took this interdependent model and we actually asked the question, what happens if on top of all your problems that you have already, what happens if things are also online? So you don't get to see the whole problem instance up front, and instead it's revealed over time. I will not get into much of the interdependent part of definitions and stuff because you have seen Divya's talk. So I'm going to focus first on this optimal stopping side or online side, say a few things on that, in case you're not well oriented in this field. Hopefully everybody's able to follow in the end. So our main problem that we're going to look at is essentially you have a sequence of numbers in the end that arrive one by one. They are ordered in some way. You see the first one, you see the second one, and so on. And well, your goal is to pick one number. You stop at some point and say, okay, this is the one I want. However, you have to pick immediately when you see a number or let that number go away. So essentially, you can't go back to something from earlier. And this makes the problem online in the sense that when you pick, you don't actually know whether you're doing very well. For example, in my picture up there, when you're trying to sell your cat to the person that values it the most or loves it the most, right? You might be pretty happy to see someone with a value of 20 and not really know that later on there's someone with a 35. So this is the type of problem that we're looking at. And there is, of course, a myriad of applications, like the famous one of hiring a secretary, or if you want to buy a house, sell a piece of art. It happens very often that people don't actually wait for you to make your decisions after you've seen them all, but they will go away and opportunities pass. So this is the type of setting. And without assuming anything on top of this online setting, you cannot do much. Look at, for example, a deterministic algorithm, and say you're an adversary that wants to make the algorithm fail. So let's say you have a lot of values of 1 that you send in the beginning up to the n-1 value. And now, if the algorithm has picked one of these, you're just going to send as the very last value something very high, right? So the algorithm completely screwed up. Or on the other hand, if the algorithm didn't pick anything, your last value that you send is a 0. So the algorithm has no chance. And even if you randomize this, it's not much better. Imagine that the ith value, for example, is n to the I, and you're picking at some point some number I, after which, well, you're not sending any value anymore. You're sending zeros from there on. And now what is happening? Of course, the online algorithm must guess the point in time exactly when this drops to 0, which is just 1 over n choice. So this setting is too hard, essentially, and you need extra assumptions. And in the literature, there is a whole number of models, and I'm just going to focus on the main directions of these. So for example, you can say, I have some prior info on how these values are going to be made. So for example, the values might be from some distributions, and so far we have assumed it's prior free. We don't know about these distributions, but what if they're given? You could also assume that you know the distribution beforehand, right? Also the arrival order. So far we've said, okay, there's this adversary and he's gonna pick the last number to come last. But you could also say, for example, this is random. You have this pool of numbers and they arrive in a random fashion. And then, of course, there is the distinction of whether or not the people that are trying to buy your cat also lie to you about their values. So this is a small overview of some of the models that you can do here. And I'm going to just introduce 2 very famous ones. First, profit inequalities. So for profit inequalities, to get around this impossibility that I introduced before, what happens is you assume I'm going to see upfront the distribution di from which each of the values is drawn. These di are independent and known beforehand. And now this is enough to achieve actually a constant approximation to the expected largest number, where you only lose a factor 2. So the algorithm for this is very simple and very famous. It's simply compute the expected largest value that you think you will see, take half of that, and only accept a number if it's at least as high as half this expected maximum. So this very simple so-called threshold algorithm gives you a true approximation. And that means, yeah, this prior knowledge helps a lot, of course. Alternatively, there's also the famous secretary setting, where you don't have any priors, you don't know how the values are made, but at least you assume there is not some conspiracy going on of people trying to buy your cat, and they're going to talk about how they screw you over by coming in a certain order. You just assume you make appointments with them, and somehow it's random who has time when, right? This is reasonable in many settings. And also this random order assumption helps similarly much, because now what you can do is you can pick to wait for a while, say a constant number of a constant fraction of the n people that come, for example, half or a third. And then you say, I'm going to look at the values that these people have. And because these are random samples from the whole set of people, this gives me a good idea what is a good value. And the algorithm that essentially waits for 1 over e times n, and then charges or sets a threshold of the maximum value seen in this sample, and only picks from the bias that arrive last, the one that is first to beat this value. This will give you a 1 over e approximation to the largest value. So also here, by just doing this one extra assumption, you're getting from pretty bad approximations, say 1 over n, to a small constant. And we're going to look at both of these settings, but adding in our interdependence between the bias. So these values are not just a value, but they are a valuation function that depends on the signals of the others. Now, as an overview, all of these things that I said here with the simple algorithms that get you from like infinity to constants, they all depend crucially on the assumption that things are independent. So especially, it is not okay if you have value 1, something being important for what is value 10. Or if you have the last value is this, if the third value was that. So there's no connection between these values. They are independent, and they are going to be just determined by the distributions in the profit setting, or just being written on some cards in the beginning in the secretary. This sounds a little bit at odds with what we're trying to do here, right? Because we are assuming interdependent values. So now the value that comes at time I depends on the others. And this might cause trouble. And indeed, I'm going to open with showing you that it does. So let's look at this example here. Let's say everybody's only interested essentially in what is the signal of the last buyer. We're going to assume the profit inequality setting. So there's this adversary, and he will send buyer n last, who is the guy with the important signal. The others, they are just going to have a value of 2 to the I if the signal of the last buyer is more than 1 minus 1 over 2 to the I, and 0 otherwise. So what this gives us is, as in the picture, a sequence of values that start with like 2, 4, 8, 16, and so on, and then go up until some point in time where they completely drop off, and from then on it is all 0. This essentially recovers the impossibility that I showed you in the beginning, when you don't have any assumption except the online scenario itself. And indeed, if you do the math on the expected values for an algorithm that tries to pick one, well, the algorithm cannot do much but guess and will get like a value of 1, while your optimum in expectation actually is something in the order of n. So this essentially is as bad as having no assumptions. And the reason for it is, of course, that you can, despite the assumption that you see the distributions beforehand, you cannot know anything about the actual values because these depend on the information of the signal n that only arrives after the sequence is over, right? So this is a relatively clear way of showing you cannot do that. This destroys your saving assumption from before. And sounds pretty discouraging to have this impossibility result, but there's not really reason to give up. So we just take this as, well, a good motivation to actually consider different scenarios. And what we're going to do is we will take 2 different types of agents, define them, and then look at whether we have agent type A or B. So the first one will be actually myopic agents. Let's say you want to say in an open auction, you want to buy something and bids are just collected publicly until somebody gets the item. Then the auction stops. In this scenario, for example, you cannot really make your value dependent on the bids of people that can never bid, right? Because the auction has stopped. So it makes sense that your value only depends on those that came before you and, of course, your own signal. And for such agent, we will just call them myopic. And these are the ones where the case that we just saw cannot happen, essentially. On the other hand, far-sighted agents will be what we had previously. They just can depend on anything, arriving earlier or later. So with this distinction, actually, there is some good news and we can do something. Let me show you a small overview of what we have. So in the end, after looking at both the settings, Prophet and Secretary, and doing them in both versions, farsighted and myopic, besides showing that you can't do better than essentially an N competitive algorithm for farsighted agents in the Prophet setting, we could actually show something much better if agents are myopic. This will give you an algorithm with a 2 times the original approximation factor, which means 2 times 2, which gives us a 4. I will show this in a little bit. We also can do pretty nice constants for secretary settings. And here, it doesn't really matter if agents are farsighted. I will also try and explain later why not. And we also get nice constants, which also note are basically the optimal constant from the original setting times 2. And finally, what we also did was look at truthful mechanisms. So we added in the requirement that instead of just an algorithm, we would have to do a truthful mechanism that incentivizes people to report their actual valuations and their actual signals. We have not looked at the case here where valuations are also private. But for private signals, we're getting essentially everywhere an extra factor of 2. And I will, at least as an example, also say something about that in the end. Okay, into our positive results. I would like to start with the Prophet setting and show you why this assumption that buyers are myopic actually helps. Just to make clear that it's totally defined what we're talking about, let's just review the setting as a whole. So we assume that the buyers are myopic. The order they arrive in is adversarial, as is normal in Prophet inequalities. We know the valuation functions. So the VI, these are public, and we are aware of them before the buyers arrive. And when one buyer arrives, we learn their signal, so the SI, which is drawn from some known distribution, DI, and the distributions are not dependent on one another, right? So the signals are independent. However, the valuations that come out of them, these, of course, depend on other people's signals. And also we will assume, because we need something to make this work, that the evaluation functions are monotone and subadditive over signals, as Divya introduced previously. This will be because we only see part of the instance, so therefore we only see part of the signals when we make decisions, and we need that to mean something for the overall value, and we need to be able to compare. So these are our assumptions, and let's just try and mimic what, well, non-interdependent profits do. As I said before, there you can essentially go and say, I will take the expected best value, I will halve it, and I will accept anything that's at least, well, half the expected optimum, right? Does that work here? The answer is sadly no. So we're trying it, and then let me just say why not. So assume that you see these myopic bias. Say the fourth one just arrived, so you know the first 4 signals, the green ones, and you know that this guy has a value of 20, which is fine, right? However, actually what you also know is something about the later arriving bias. So even now, if you have that the threshold, say, is 10, and your current value beats it, it might happen that you already basically know when evaluating the other bidders that you don't have yet, because you see their functions, over the signals you already have, so the green part of the signals, this lower bound might already be better than 20. For example, here for the red box, it's already 65. This means an adversary can make valuation functions in the way that later bidders are always better, right? And arbitrarily better. So you have to take that into account. You cannot pick the 20 now without losing too much. And this is essentially why you have to do more than in normal profits. I hope this is okay. Ask me questions at any time. I need to go back. Somehow this jumped like a lot of slides. Okay. So what we do for this is, well, we look at it, and if someone's better in the future, and we already see that, we're going to wait and take him instead. Right? This is the only thing we add. So with that, actually, we can show a constant, and it's, as I already spoiled, it's 4. I would like to just take a second to give you some sense of why. So let's say we want to show the performance of this. And let's say I star is, in the end, the best agent. We evaluate the best agents, of course, only on the I star first signals, because everything is myopic by assumption. And then we can say, okay, what is the expected value over the guy? It's what we expect him to be worth if we never stop, right? Plus what we expect him to be worth when we stop. And because of subadditive, we can do that as 2 parts, which is essentially the part up to signal t, and then on the right-hand side, the part later than signal t, where t is the time where the algorithm actually stopped, which might have been too early. And now let's try and bound these values. So actually the first one is, well, if the algorithm never stops, that is because no one is as good as half the expected optimum, right? So we can say if x is half the expected optimum, that we can bound it like this. The second part, well, this is the value that we actually see in the algorithm and that we pick the current maximum at. So time t, we look at what is already there in values and we pick the best. So this is something we actually realize in the algorithm. And then the last part, we can only bound by being not more than essentially the optimum. So 2x we write. Let's put this together. So we can write this if we replace the left-hand side with the expected opt by just 2x, which is the same as 2x mod equal x plus the expected algorithm gain plus the probability that we stop before infinity times another x. Let's bound the right-hand side of this also by expected algorithm value, because we already did that before above. And then essentially this reduces to 2 times alg is greater or equal x. And because x was 1/2 the expected optimum, well, we get a 4. So this is not too hard. And shows that it's actually for myopic bias possible to get a nice small constant that is not too bad, right? Where the extra factor essentially comes from this, well, you only see a part of the signals, might be the wrong part of the signals. And we have the actual interdependence assumption on top of the original profit inequality problem, but it's not too bad. So yeah, this is a nice positive result. And as I said, we have more of them. We also did the secretary problem and tried to add interdependence on top of that. So here, our algorithm that we use was a little bit more intuitive in the end. We sample the first N/E agents as the original also does. And then on arrival of someone after the sampling phase, we will stop if their value evaluated on the signals we have yet is the best of all the betas we've seen. So this is very reminiscent of the original algorithm, just taking into account the part of the instance we already know. What is different here actually? Why can we just do this? This looks simpler, right? And indeed, in the secretary setting, we are a bit more lucky because now it's not possible for an adversary to hide a good signal or a good agent at the end, because the values are adversarial, yes, but then there is this random mixing of the order that will possibly make us see this very early on. And then also, if you fix any agent that, say, comes after a constant fraction of the other ones, then by subadditivity, you have that the value of this agent evaluated on the so far signals gives you a constant factor approximation to the overall value in expectation, because these signals that you evaluate them on, these are determined at random via the random order. So actually, the myopic value of someone is an approximation now to the far-sighted value, which will give us that we can now do the far-sighted version. And finally, we have also, which we exploit in the proofs that I'm not showing, that if we pick by a rule that defines our maximum so far, as we do above, right, then the probability that we stop in a certain step is just a fixed number. And it doesn't matter which part of the instance we see until then, it's going to be always the same probability for stopping in step I. So these are the things we essentially throw together to get our 2E approximation for secretary. Also, despite the valuations, of course, still being visible when we see an agent, we do no longer need them before arrival of the agent. Because now, as we've seen here, everything is evaluated essentially only for things that have already arrived, including the valuations. So this is like a slightly more general model that we can do at the same time. I have written it down here as an overview. So the model difference to the profit setting that we can achieve with the secretary assumption is that also the valuation functions only become public at the point the buyer arrives. And we can, as I said, now also approximate in the far-sighted setting. So agents can depend on the signals of later agents. Okay, this is the second to last thing I wanted to say. And since Divya's talk was so into mechanism design, of course, we also tried to do that. So let's consider this extra requirement of truthfulness. What happens now, we assume that the signals are agents' private information, and they might lie about them, right? Which means that our mechanism should be truthful in exactly the same EPIC sense that Divya introduced. So we will also do ex-post incentive compatibility. And there is a problem when you want to implement this. And this problem is essentially our algorithms. What do? They look at the best values so far, and they try to pick that, right? And this might be influenced by misreporting a signal. Let me show how. So let's, for example, look at the profit algorithm. And the profit algorithm, as you recall, maybe had just this threshold. You have to beat it to win, but also you have to be better than any other agent that comes later, evaluated on the signals that are already known. And this last part is a problem, right? What if there is a good guy later and he depends on your signal? So you don't want him to win, you want to win yourself, and you might report a lower signal, for example, to make that happen. So the second part is moving away from the original profit, where it's just a threshold, you charge that as a price, you're golden, and it makes us manipulable. So we have to fix this. However, we have the threshold in there somehow, which was in the original given just a natural pricing algorithm. So there is some hope. Let me just give you a very short example here. So let's say we have this guy again at step 4, has a value of 20, his signal is 10. But in step 6, there will be this other guy whose value is just 10 times the signal of the 4th, which gives you 100, right? So we know in step 6, we see 100, and we won't pick the 20, although the threshold is only 10. Now, of course, number 4 will try and give us a lower signal instead to keep us from getting the 6th guy instead. So he might just say, oh no, my signal is 1. This would make the value of the 6th buyer only 10. And now, even if the misreporting also changes the value of the 4th buyer, remember we don't have single crossing or the like, even if so, he might suddenly win the game, and we want to keep that from happening. So for this issue, what we came up with to deal with it is as follows. We changed the algorithm a little bit. As I said, the problem is this second part, where we go and look for better future buyers. And we just essentially lose some approximation and kill off this second part from the reach of the manipulation by the current agent. We do this as follows. So we will still look at the arriving buyer, compare him to our threshold X, and only consider him if he beats X. But then we don't look into the future and decide depending on that. We're just gonna say, okay, you're getting it with some probability 1/2. We just flip a coin. And if the coin comes up positive, we give it to the current buyer, we charge him the threshold as a price. He wins, that's it. However, if the coin comes up negative, we will try and find someone later who has a better value and give it to them. Now it is not influenced by the report of the current buyer, which one of these options we take, right? However, we might take the wrong one approximation-wise, which is why, well, we end up with an extra 2 in our factor. Okay, this is all I wanted to show. Here is the overview again of what we have so far. Of course, this is the groundwork. We only looked at the very most central settings, and we're hoping that in the future, it might be possible to do a lot more. For example, our constants are just what we found, and largely we can't show that they're tight, so probably you can do better. You might look for more lower bounds and impossibility results to back up this loss that we have with respect to the original models without interdependence. And also, of course, there's a lot of variations to these 2 very basic settings where you have k-cats to sell. There is a matroid constraint going on. There is some other feasibility constraint. You might want to look into combinatorial options. All of these things are completely unresearched for now and interesting directions in the future, I believe.